What we do here is go back.
Imagine using GarageBand or Audacity to make music. Couldn't be me.
Providing protection and a sleek look.
Don't you wish you could simply move your fingers and make gestures? It'd be as simple as...
Let's go!
Whoa. Does this ever happen to you?
Essential tremor, or ET as we'll call it, is a common neurological disease resulting in uncontrollable shaking, primarily in the hands. It affects nearly 4 in every 1,000 people worldwide, has no real cure, has a 50% chance of being passed down genetically, and worsens with age, with the potential of developing into Parkinson's or other diseases. ET causes difficulty in many daily activities such as writing, eating, or drinking.
Our team proposes the torque-induced tremor stabilizer, a wearable assembly needing Keras, Myoware EMG, and other Flywheel fixtures. Leveraging gyroscopic stabilization to reduce the perceivable effects of tremor, the inertia produced by a weighted flywheel resists displacement along its plane of rotation. While not new in its own right, looking at current solutions in the market, the designs show promise, but with a few drawbacks. For one, the size of the apparatus is quite chunky, leading to an awkward, obtrusive feel. Another issue is due to the gyroscope actively correcting for changes in its stabilization plane, movement of the hand has been described to feel, quote, like mud. Our product instead aims to combine gyroscopic stabilization with a machine learning algorithm to deliver an effective and responsive mitigation effect. This aims to be packaged in a comfortable and sleek enclosure to minimize the footprint.
With our idea in place, what could possibly go wrong?
I think it really depends on good coupling.
For the onboard electronics, we have an Arduino Nano as our microcontroller for its small form factor and computational power. Our sensors consist of a combination of an MPU 6050 IMU sensor and a Myoware EMG sensor to record and stream the movements of the user as well as the muscle activity. The onboard accelerometer/gyrometer allows us to understand the orientation of the user's hand as well as pick up on macroscopic movements. To aid in the measurement of tremor, we use an EMG sensor to sense the neural impulses of the underlying muscle, which was helpful when the user grasped at an object or rotated the wrist. Spinning our flywheel is the iFlight Zing E 2400 kV brushless DC motor. Now this puppy is capable of revving up to 41,000 RPM and producing 0.3 Newton meters of torque, allowing the flywheel to accelerate up to operational speeds in under a second. Now of course, every Epic Gamer setup needs the all-important RGB lights, so no expenses were spared in the aesthetics department. LED strips line the inner wall of the flywheel enclosure to ensure all the spicy details are illuminated and make the glove the absolute centerpiece of the room.
The software portion of the project was concerned with effectively using the 7 sensor inputs to classify tremors and determine a good motor response speed. Because of the large number of inputs, we decided to use neural networks to try to capture the full range of cases. Also, since making a multiple output neural network on the same set of inputs was unnecessarily convoluted, we made 2 networks instead. A simple one to figure out when tremors are occurring, and a more complex one to determine the motor driving speed at a given time. Our hope was to be able to shove the inputs from any instance into the network and have it run the motor at the appropriate speed while also maintaining an acceptable degree of accuracy. The motor speed model uses deep Q-learning, which associates certain network inputs with a reward value. The network evolves to maximize the reward, which corresponds to optimizing the input with which it is associated. In our case, maximizing the reward meant minimizing the gyroscope inputs from the direction normal to the plane of the hand. A lot of our time was also spent on testing and training the network models. To this end, we developed algorithms which could send data to the model from static databases as well as from live feeds. Finally, we developed a simple methodology to translate a neural network to a set of matrices and functions which could be used to transfer the model to a less powerful controller such as the Arduino Nano.
The majority of the mechanical goods are stored within the enclosure. The flywheel is laid from solid steel, which was selected for the density to generate the inertia required to counteract the forces of the hand tremors. The flywheel and the motor were mounted to a water jet cut aluminum swing bracket, with the shaft pressure fit into ball bearings to further reduce the vibrations. But of course, having 150 grams of mass destruction on the back of your palm makes you more dangerous than Ben 10, so appropriate protection is needed. With a composite sandwich panel of aluminum, rubber, and more aluminum, this bad boy could protect Indiana Jones from a nuclear blast. Furthermore, gaskets, velvet lining, and caulk help insulate this enclosure from sound vibrations, just like the noise-canceling ability of today's sponsor, Raycon. Whether I'm researching motor torque or in the iGen shop running the bandsaw, I can always rely on the top-notch sound quality and battery life to get me through the day. Go to buyraycon.com/TTW for a 15% discount off your next order. Link is in the description. Both halves of our clamshell design seal tightly together to minimize sound escaping, before being sealed by a shatterproof lid. An 1/8 inch of polycarbonate protects the enclosure from any potential oopsies, while still allowing you and everyone around you to examine the beauty of our assembly.
To first test the validity and safety of the device, a test stand was proposed and designed to simulate the movement of the hand. Atop the stand stood the only thing keeping everyone in the room safe, a 3D printed motor mount which could swing in the forward-reverse direction while being constrained along the axis of tremor. This was the bastion of humanity, the Jesus nut restraining the Beyblade of Doom from running rampant in the immediate vicinity. A Scotch yoke mechanism would be used to adjust amplitude and frequency of the tremor. Yeah, that didn't work. A separate motor would fling a small weight to create the tremor. Yeah, that didn't work either. To first test the validity of the device, a volunteer would have the motor mount duct taped to their hand and would be asked to perform a series of movements, such as tilting the hand or picking up an object. From this, we confirmed that the angular momentum was capable of cancelling out displacement along the longitudinal axes, and the swing was able to prevent gyroscopic precession from torquing the user's hand in their own face. So, we redesigned our test stand and came up with Clement instead. We used the Clement test stand to gather data and test how fast we need to go.
So, what's next in store for the project? In order to effectively respond to changes in the motor, we would want to purchase an ESC which is able to reverse the input current to the motor. This can greatly reduce the time between the startup of a motion and the speed reduction in response. As well, we would want to capture a wider sample set of data from a variety of trial participants, allowing for the neural network to have more samples to train on, thus making it more accurate and robust. Looking a bit further ahead, optimizing the weight of the glove would help it feel less unwieldy, which can be achieved by using a stronger, lighter material for the enclosure, or by reducing the weight of the flywheel. Alternatively, the system could be made less reliant on a gyroscopic stabilization, instead opting to use denser, smaller weights, or even resistance bands to reduce the tremoring effect. Oh yeah, we also beta tested funtime mode.
That's really cool, that response on that. But yeah, like John was saying, to couple it more